Right, yesterday we talked about what slope means, right? We said it was the rate of change. So if you put a plant outside in the sun, how much time is it going to take for it to grow, let's say, 2 inches? Okay? So that's the rate of change. It's how fast change happens. Now, to find the slope of a curve like this one is a process that you've been doing ever since pre-algebra, maybe even before that. So suppose you're given a linear curve. So notice we're talking about a linear curve at this point. You're given a linear curve such as this one, and you want to find the slope at a specific point. 3, 5, for example. So at this point is where you want to find the slope. What we can do is we can pick 2 other points that are near the point that we want, and we can find the slope between those 2 points. In this example, I've chosen this point, the coordinates of which are what? X is 5, and the y value is 7. So here, x is equal to 5, y is equal to 7. Okay? Now, normally we would write that as 5, 7, or x, y. Now, let's just change up our notation a little bit. If this is x, and if this is the y value of it, I could also say that if this is x, then this is f of x, right? So if this is the point x equals 5, then this one is f of 5, which is 7, right? So if this is x2, then here this one is f of x2. Okay? Now, let's go to my other point. Here, this is x equals what? 1. And here, this is f of 1, or f of x1. So this is x1, and this is f of x1. So now, instead of x1 and x2 and y1 and y2, we have x1, x2, f of x1, and f of x2. That's going to replace our y1, y2 from now on. Now, what I'm going to do is find the slope between those 2 points. And when I find the slope between those 2 points, it'll be the same as the slope at this particular point. Okay? So how much does the y value change when I go over this many units in the x? Okay? All right. We're usually used to finding the slope with this formula, y2 minus y1 over x2 minus x1. But we said that we're going to make it more elegant, so it's going to be, actually this should be f of x2 minus f of x1 over x2 minus x1. Okay? And now, what's f of x2? It's 7. What's f of x1? It's 3. So 7 minus 3 over 5 minus 1 is 1. Okay? So the slope between these 2 points is 1. So let's recap what we did. We had to find the slope at this point, 3, 5. The way we did that is we chose 2 points, one before it, one after it. We found the slope there, okay? And that will give us the slope at this particular point. Now, what if I had chosen 2 different points? What if I had chosen this one and this one? Would my slope have been any different? No. What if I had chosen the point itself and this one? Would the slope have been any different? No. If I had chosen 2 points here that not even related to that region, would the slope have been any different? No. Because this is a linear curve, the slope anywhere around here is linear, is the same. All right? So no matter where I am here, it doesn't make a difference where I find the slope. When the curve is not linear is when we get into trouble. All right. Suppose now we're given the curve f of x equals x squared. And we would like to find the slope at this point, 1, 1. Okay? What I'm going to do is I can do the same thing. I can pick 2 points to find the slope. However, things get tricky here because depending on where I am exactly on this curve, the slope is going to be different, right? So if I'm here, imagine you're walking up this. If you're here, there's practically 0 slope. If you're here, the slope is different than if you're here. Okay? So look at what the slope is like here. That's what it looks like. Look at what the slope looks like here. Do you see how these two have different steepnesses? That means the slope here is different than the slope there. So it makes a difference which 2 points I pick to find the slope. Now I want to find the slope of the curve at this point right here. So let's see what we're going to do. What we did before has to be modified somewhat in order for us to get the most accurate answer. Okay? So in this case, I choose 2 points. One here and another one here. And I find the slope between this line. That formula, y2 minus y1, can only work if you have a straight line. So I try to find the slope between these 2 points, and I get that the slope is 4. Okay? But you know what? That's not really an accurate representation because the slope is changing all the time. So look at what I do here. I bring this point closer to my first one. When I bring the point closer to it, the line through them changes somewhat. And when I find the slope of that, I get a value of 3. So that's a different value. What I do is I bring the point even closer to my first point. So now I have 1, 1, and then I have 1.1 and 1.21, right? And I find the slope there, and look at how dramatically the change looks, right? So we went from a slope of 4 to a slope of 2. So the trick is then, if I really want to zero in on this slope and get the most accurate and precise approximation of it, I have to get my points infinitesimally close to each other, extremely close to each other. Okay? Only then will I get the most accurate version of the slope. Any questions here? So let's talk about some more terminology. What we're doing is we're picking 2 points and we're drawing a line in between them. Now, when you have a line that passes through a curve at 2 distinct points, that line is called a secant line. Okay? Anytime. So suppose you have a curve that looks like this, and you draw a line that passes through the curve and touches it at 2 distinct points. That line is a secant line. So that's what we're doing here. We're picking 2 points. We're drawing a secant line in order to find the slope of it. Okay? So here, we brought the point closer and closer and closer. So look at exactly how far apart these 2 points are. In this case, one has an x value of 1, another one has an x value of 3. So look, they're 2 spaces apart, right? We brought now the point closer so that it's only 1 space apart. Finally here, we brought the points so close to each other. How far apart are they? 0.1. But in terms of calculus, 0.1 might as well be 5,000 miles away. Even that is a very big distance. So now we have to bring the 2 points even closer. Not 0.1 spaces apart, or maybe 0.000000001 space apart. So close that they're practically not even apart. That's the trick. That's when we get the most accurate approximation of the slope. Okay? So, As the two corner points move closer and closer, the secant is giving us a better and better approximation. Now, the most accurate approximation is going to be a tangent line. So let's just explore here what we're doing. So suppose you want to find the slope at this point. Okay? You pick this as one of your points, and now you go some distance apart and you pick this as another point. Okay? Now, this is my x value, right? Now stay with me here. I go a few units away and I call this distance h. Okay? Now, if this is a value of x, okay, what would that value be? So if this was x and I went over h spaces, where am I now? X plus h. Okay? Now, suppose now I say to myself, you know what? H is too big. They're really too far apart from each other. I'm going to make h much, much smaller. So suppose I make h a lot smaller. So now that's h. What's this point now? Now that point is x plus h. Okay? And as I make h smaller and smaller and smaller, these 2 points will get closer and closer and closer. Well, how small are you going to make h? You want to make h almost 0. Okay? It's like you love somebody so much, you want to get so close to them, you're 0 centimeters apart from them. That's what we want to do. We want to get these points so close to each other, they're 0 centimeters away from each other. That's exactly what we're doing. Okay? How do we express that in math? And we don't say, I want to get it so close, h is almost 0. We can't say that. The best we could do is, we want h to be almost 0. That looks like limit, doesn't it? So it's the limit of something as h is almost 0. Okay? So what happens when h is 0? Let's see. Before, when our first point was here, here was the y value, and my secant line looked like that. Okay? Now, when h is very, very small, where is my other point? Let me try to do it here. When h is tiny, then my other point is almost on top of the first point, right? Now if I connect those 2 points, the red and the yellow, what is that line going to look like? This. Okay? So what did we say the red line was? What name did we give it when it crossed the... It's a secant line. But when the points are so close, they're almost on top of each other, and I connect those 2 points, the line becomes a tangent line. Okay? And now, when I find the slope of the tangent line, that's the best approximation of the slope of this curve at that point. Alright, so this was our f of x. Okay? And this used to be, when this was x plus h, this now is f of x plus h. Okay? So remember we had x1 and x2, and then we had f of x1 and f of x2. Now, this is x, this is x plus h. So this is f of x, and this is f of x plus h. Okay? When we move the point closer, f of x plus h is now very, very close to the first one, f of x. So now, how are we going to find the slope then? We had said that the slope was y2 minus y1 over x2 minus x1, and then